Part 1, The Invitation. Close your eyes for a moment. Not because you need to sleep, not yet, but because what I'm about to tell you requires a kind of openness, a willingness to let go of everything you think you know about the world around you. The chair beneath you, the air you're breathing, the darkness behind your eyelids, all of it, every single atom of it, is stranger than you can possibly imagine. And tonight we're going to explore exactly how strange. This is the story of quantum mechanics. It is, without question, the most successful scientific theory ever devised by human beings. Its predictions are accurate to more decimal places than any other theory in the history of science. The technology built upon its foundations has transformed civilization, from the microchips inside your phone to the lasers that read your music, from MRI machines that see inside your body to the GPS satellites orbiting silently above your head right now. And yet, not a single physicist in the world will tell you they fully understand it. Richard Feynman, one of the greatest physicists of the 20th century, once said that if you think you understand quantum mechanics, you don't understand quantum mechanics. That wasn't a joke. That wasn't false modesty. That was an honest admission from a man who spent his entire life working with these equations, building these theories, winning the Nobel Prize for contributions to this very field. The quantum world does not play by the rules we were born understanding. It does not behave the way objects on a human scale behave. It is, in every meaningful sense of the word, alien. And that alienness is not a flaw in our understanding. It is the truth itself, verified again and again by experiment, confirmed by the most rigorous testing science has ever conducted. So tonight, we're going to travel together into that alien landscape. We'll begin at the beginning, with a puzzle so simple it seems almost childish, and yet so deep it took the greatest minds of the 20th century decades to even partially resolve. We'll move through the strange territory of waves and particles, of superposition and entanglement, of cats that are somehow both alive and dead, of particles that seem to communicate faster than light, of a universe that may not have a definite reality until someone looks at it. We'll explore what the quantum world tells us about the nature of time, the nature of consciousness, the nature of reality itself. We'll sit with the philosophers and the physicists as they argue, sometimes bitterly, about what these equations actually mean for the world we live in. And somewhere along the way, you may find that the world you thought you lived in has quietly dissolved, replaced by something far more mysterious, far more beautiful, and far more strange. Let's begin. Part 2, The Problem with Light. To understand quantum mechanics, we need to go back to the late 19th century, back to a world that was, scientifically speaking, very nearly confident. By 1890, physics had achieved something remarkable. The laws of motion formulated by Isaac Newton 2 centuries earlier had been tested and confirmed in every domain imaginable. They predicted the movements of planets with extraordinary precision. They explained the behavior of gases, the trajectory of cannonballs, the oscillation of pendulums. Newtonian mechanics was so powerful, so reliable, that many physicists of the era genuinely believed the work was nearly done. James Clerk Maxwell had recently unified electricity and magnetism into a single elegant framework, Maxwell's equations, and from those equations had derived the existence of electromagnetic waves traveling at the speed of light. Light itself, it turned out, was an electromagnetic wave, and waves were well understood. Waves were classical. Waves made sense. The universe, it seemed, ran on two kinds of things, particles and waves. Particles were little discrete chunks of matter, tiny billiard balls obeying Newton's laws. Waves were disturbances in a medium, ripples in water, vibrations in air, oscillations in the electromagnetic field. The two were completely distinct. Everyone knew the difference. The mathematics was clear. And then came the light. Not light in general, that was fine. The problem was a very specific kind of light, the light emitted by hot objects. When you heat a piece of metal, it begins to glow. Heat it enough and it turns red, then orange, then yellow, then white. The color changes as the temperature increases, and this wasn't mysterious, everyone knew this. What was mysterious was the precise shape of the spectrum, the exact distribution of energy across different frequencies of light emitted by a perfectly absorbing object. What physicists called a black body could not be explained by classical physics. Every formula derived from classical wave theory produced the wrong answer. One formula worked reasonably well at low frequencies, but catastrophically failed at high ones, predicting that a hot object should emit infinite energy at ultraviolet wavelengths. Physicists called this the ultraviolet catastrophe. If classical physics were correct, every warm object in the universe, including you, lying there right now, should be constantly radiating infinite amounts of energy in the ultraviolet range. The universe should be blindingly, lethally bright at all times. Obviously it isn't, so something was wrong. In 1900, a German physicist named Max Planck found a formula that worked. He worked backwards from the experimental data and found a mathematical expression that correctly described the black body spectrum at all frequencies. But to make the formula work, he had to introduce something deeply uncomfortable. He had to assume that energy was not continuous. In classical physics, energy was like water. You could have any amount of it. A wave could carry any quantity of energy, varying smoothly and continuously. But Planck's formula only worked if energy came in discrete packets, indivisible chunks, minimum units below which you could not go. He called these packets quanta, from the Latin word for how much, and the size of each quantum was related to the frequency of the radiation by a constant, a tiny, universal number that now bears his name, Planck's constant, written as the letter h, one of the most important numbers in all of physics. Planck himself was uncomfortable with this idea. He thought it was a mathematical trick, a convenient fiction that happened to produce the right numbers but didn't reflect physical reality. Surely, he thought, someone would come along and explain it properly, in terms of good, clean, continuous physics. That someone never came. Instead, 5 years later, a young patent clerk in Bern, Switzerland took Planck's uncomfortable idea and made it far more radical. His name was Albert Einstein. Part 3. Einstein and the Photon. Einstein is famous for relativity. But if you asked physicists which of his 1905 papers was truly the most revolutionary, the one that broke the most fundamental assumptions of physics, many would say it wasn't the paper on special relativity. It was the paper on the photoelectric effect. The photoelectric effect had been observed for years. When you shine light on certain metals, electrons are ejected from the surface. This was known. What was strange was the way it happened. Classical wave theory made clear predictions. Brighter light carries more energy. So if you shine brighter light on a metal, the electrons should be ejected with more energy. They should come flying out faster. And if the light is too dim, you might have to wait a while for enough energy to accumulate before any electrons are ejected at all. But that's not what happened. What actually happened was this. The energy of the ejected electrons didn't depend on the brightness of the light at all. It depended on the color, the frequency. Dim blue light ejected electrons with more energy than bright red light. Below a certain frequency of light, no electrons were ejected, no matter how bright the light was. And when electrons were ejected, they came out immediately, no waiting period, regardless of how dim the light. Classical wave theory had absolutely no explanation for this. Einstein did. He took Planck's quantum idea and extended it from radiation to light itself. Light, Einstein proposed, wasn't just emitted in discrete packets. It existed as discrete packets, individual particles of light, each carrying a fixed amount of energy determined by its frequency. When light hits a metal surface, it's not like a gentle wave gradually accumulating energy. It's like a hail of tiny bullets. Each particle of light either has enough energy to knock out an electron, or it doesn't. Brighter light just means more bullets, more particles, but each one carries the same energy as before. And when a particle hits, the collision is immediate. There's no waiting. These particles of light are what we now call photons. Einstein won the Nobel Prize for this discovery in 1921, not for relativity, for the photon. And with the photon, a deep problem was born. Because here's the thing, light was unquestionably a wave. Maxwell's equations proved it. The phenomenon of interference, where two light beams combine and cancel each other out in certain places, proved it. You cannot explain interference with particles. Particles don't cancel each other. Only waves do. But now Einstein was saying light was particles, individual, discrete photons. So which was it, wave or particle? The answer, it turned out, was both, and neither. And that answer would take the next 2 decades to even begin to unravel, and in some sense, we are still unraveling it today. Part 4, the double slit. There is an experiment so simple you could describe it to a child, and yet so profound that Richard Feynman called it the only mystery of quantum mechanics, the one from which everything else in the theory follows. It is called the double slit experiment. Imagine a wall with 2 narrow slits cut into it. On the other side of the wall is a screen, like a photographic plate that records where particles land. Now, you fire particles at the wall. Let's start with something obviously particle-like, tiny marbles. When you fire marbles at a wall with 2 slits, the pattern on the screen behind is exactly what you'd expect. 2 bands of marks, each one directly behind one of the slits. The marbles that go through the left slit land on the left. The ones that go through the right slit land on the right. Simple, intuitive, completely in line with everything you know about how the world works. Now let's do it with light. You shine a beam of light at a wall with 2 slits, and on the screen behind you don't get 2 bands. You get an interference pattern, a whole series of alternating light and dark stripes spread across the screen. Bright where waves from the 2 slits arrive in step with each other and reinforce. Dark where they arrive out of step and cancel. This is wave behavior. Classical, expected, perfectly understood. Light is a wave. Now here's where it gets strange. Do it with electrons. Fire a beam of electrons at a double-slit barrier and look at the pattern on the screen. You get an interference pattern. The same stripes. The same alternating bright and dark bands you get with waves. These particles, these little chunks of matter, are interfering with each other, creating a wave pattern. Interesting, strange, but perhaps understandable. Maybe electrons in a beam somehow interact with each other, creating wave-like effects. Maybe it's a collective behavior. So let's test that. Fire 1 electron at a time. 1 single electron, then wait, then fire another. Each electron hits the screen and leaves a single dot, a single particle detection. 1 dot, then another, then another. They seem to be landing randomly. But wait long enough, fire enough electrons, one by one, and the pattern of dots begins to reveal itself. Slowly, out of what seemed like randomness, the interference pattern emerges. Bright bands where dots accumulate, dark bands where almost no dots land. The electron, traveling alone through space, with no other electron to interfere with, somehow produces an interference pattern. It interferes with itself. This means the electron doesn't travel through one slit or the other. Somehow, impossibly, it travels through both slits simultaneously. It exists as a wave spread across space, passes through both openings, interferes with itself, and only when it hits the screen, only when we detect it, does it become a single particle at a definite location. But wait, we can check this, can't we? We can put a detector at the slits, watch which slit each electron goes through. Surely we'll see it go through one or the other. So the experiment is done. Detectors are placed at the slits, watching. And the interference pattern disappears. The moment we watch which slit the electron goes through, it stops going through both. It goes through one or the other, like a normal particle, and the screen shows two bands just like the marbles. The act of observation changes the behavior of the electron. The act of measurement destroys the quantum effect. This is not a limitation of our instruments. It's not that our detectors are disturbing the electrons in some solvable mechanical way. This is a fundamental feature of reality. The quantum world behaves differently depending on whether it is being observed. The very concept of which path did the particle take turns out to be undefined, meaningless, unless we actually look. And this single experiment contains, in miniature, the entire philosophical earthquake that quantum mechanics represents. Part 5. Superposition and the wave function. To make sense of what we just saw, or to at least describe it mathematically, even if we can't visualize it, physicists in the 1920s developed a framework, a set of equations and rules that could predict the behavior of quantum systems with extraordinary precision. At the heart of this framework is an object called the wave function. The wave function of a particle is a mathematical description of its quantum state. It doesn't tell you where the particle is. It tells you the probability of finding the particle in any given location if you were to measure it. The wave function spreads out through space, representing not a definite position but a cloud of possibilities, each one weighted by its probability. This is called superposition. A quantum particle in superposition isn't hiding in one definite place and we just don't know where. It genuinely exists across multiple possibilities simultaneously. The positions are not hidden from us, they're not definite at all. The particle is, in a very real mathematical sense, everywhere its wave function has a value all at once. When you measure the particle, when you detect it, the wave function does something strange. All those spread out possibilities suddenly collapse to a single definite outcome. The particle is found at one specific location. The wave function has collapsed. This process, called wave function collapse or measurement, is one of the most debated and mysterious aspects of all of physics. Before measurement, a spread out superposition of possibilities. After measurement, a single definite outcome. The transition between them is abrupt, and the equations of quantum mechanics don't describe it. They describe the evolution of the wave function beautifully, with exquisite mathematical precision, right up until the moment of measurement. And then they say nothing. What actually happens during measurement? Why does the wave function collapse? Why does one outcome happen rather than another? These questions don't have agreed-upon answers. Physicists have been arguing about them since the 1920s, and the argument continues to this day. What quantum mechanics does give us is this: a rule for calculating probabilities. You take the wave function, square its amplitude at each point in space, and that gives you the probability of finding the particle there. This rule, called the Born rule, works flawlessly. Every experiment confirms it. The predictions are perfect. But what does the wave function actually represent? Is it a physical thing, a real wave rippling through space? Or is it just a mathematical tool for calculating probabilities, a description of our knowledge, not of reality itself? Niels Bohr, the Danish physicist who was perhaps more responsible than anyone for shaping the interpretation of quantum mechanics in its early decades, would have said, "Don't ask. The question is meaningless. Quantum mechanics gives us a tool for predicting the results of measurements. Reality between measurements is not a physical question, it's a philosophical one, and physics doesn't do philosophy. Measure, calculate, predict. Shut up and compute." This view, sometimes called the Copenhagen interpretation, after Bohr's city dominated physics for most of the 20th century, and it drove Einstein absolutely mad. Part 6. Einstein's Objection. Einstein never accepted quantum mechanics. Not fully. He accepted that it worked, he could hardly deny the experimental evidence. But he believed, with deep conviction, that it was incomplete, that somewhere beneath the probabilistic equations was a layer of reality that was definite, deterministic, real. He famously said that God does not play dice with the universe. by which he meant nature doesn't actually operate on pure randomness. The probabilities of quantum mechanics must be hiding something, hidden variables, perhaps, definite underlying states that quantum theory doesn't have the tools to see. Bohr reportedly replied that it was not Einstein's place to tell God what to do. The two men sparred intellectually for decades. They had enormous respect for each other, genuine warmth, but on this question they could not agree. Einstein spent years crafting thought experiments designed to show that quantum mechanics was inconsistent, incomplete, or paradoxical. Bohr spent years refuting them. The most famous of these thought experiments came in 1935, in a paper Einstein wrote with two colleagues, Boris Podolsky and Nathan Rosen. The paper described a situation that became known as the EPR paradox, and it pointed to something so strange, so apparently impossible, that it haunted physics for the next 3 decades. The EPR paper described two particles created together in a special way, correlated, linked, entangled at the moment of their creation. According to quantum mechanics, certain properties of these particles, like their spin, are not determined until measured. But the two particles are correlated. If you measure one and find it spinning one way, the other must be spinning the opposite way. Now separate the particles by a vast distance. Measure one. Instantly, the other is determined. How does the second particle know what happened to the first? If their properties weren't determined until measurement, how does measuring one instantaneously affect the other, even across light years of space? Einstein called this spooky action at a distance, and he was appalled by it. It seemed to violate the very principle of locality he held sacred, that nothing can influence anything else faster than the speed of light. Information cannot travel instantaneously. Reality must be local. Einstein concluded that quantum mechanics was therefore incomplete. The particles must have had definite spin values all along, determined at the moment of their creation, hidden variables that quantum mechanics simply didn't account for. There was no spooky action. There was no instant connection. The particles were like a pair of gloves separated before anyone looks at them. When you open one box and find a left glove, you instantly know the other box contains a right glove. But that's not magic, that's just correlation. The handedness was determined from the start. It was a beautiful argument, and for 30 years there was no way to test it. Then came John Bell. Part 7, Bell's Theorem. In 1964, a Northern Irish physicist named John Bell did something remarkable. He proved a theorem, a mathematical result, that transformed Einstein's philosophical debate into an experimental question. Bell asked, if Einstein is right, if the particles really do have definite hidden properties from the start, like the gloves, what predictions would that make about measurement outcomes? And how would those predictions differ from the predictions of quantum mechanics? The answer was subtle, and it required measuring correlations between the particles in multiple different orientations. But Bell showed that any theory based on local hidden variables, any theory that assumed particles had pre-existing definite properties and that nothing could travel faster than light, had to satisfy certain mathematical inequalities, now called Bell inequalities. Quantum mechanics predicted that these inequalities would be violated. The correlations it predicted were stronger than any local hidden variable theory could produce. This was testable, this was physics. Throughout the 1970s and 1980s, a series of increasingly precise experiments were conducted, most famously by the French physicist Alain Aspect and his team. They created entangled pairs of photons and measured their correlations in exactly the way Bell had prescribed. The results were unambiguous. The Bell inequalities were violated. Quantum mechanics was right. Local hidden variable theories were ruled out. The universe is not like the gloves. The particles do not have predetermined hidden properties. The correlations are real, immediate, and stronger than any local explanation can account for. Something genuinely non-local is happening, something that connects distant particles in a way that cannot be explained by any information traveling between them. Einstein was wrong. God does play dice, and the dice, it seems, are entangled across the universe. Elaine Aspect shared the Nobel Prize in Physics in 2022 for this work, 58 years after Bell's theorem and nearly 90 years after the EPR paper. Physics moves slowly when the questions are deep enough. But here's the important subtlety. Quantum entanglement, while real and non-local, cannot be used to send information faster than light. This was crucial, and it preserved relativity. When you measure an entangled particle, you get a random result. Your partner measuring the other particle far away also gets a random result. Only when you later compare your results through normal, slower-than-light communication do you discover that your results were correlated. The non-locality is real, but it hides inside randomness. You cannot exploit it to send a signal. Entanglement is real. Faster-than-light communication is not. And yet something connects those particles. Something we don't have words for. Something that is neither a particle nor a wave nor a signal, but something else entirely, a feature of the quantum world that has no classical analog, no everyday equivalent, no comfortable metaphor. We call it entanglement, and we're still learning what it means. Part 8. Schrödinger's cat. In 1935, the same year Einstein published the EPR paper, another physicist was wrestling with the implications of quantum superposition. His name was Erwin Schrödinger, and he had helped create the very equations at the heart of quantum mechanics, the wave equation that bears his name. But the more he thought about what those equations implied, the more troubled he became. He devised a thought experiment, a deliberately disturbing one. Imagine a cat placed inside a sealed box. Inside the box, alongside the cat, is a tiny amount of radioactive material, just enough that there is exactly a 50% chance of one atom decaying within the next hour. If the atom decays, a detector triggers a mechanism that releases a poison, killing the cat. If the atom doesn't decay, the cat lives. Now close the box and wait an hour. According to quantum mechanics, the radioactive atom is in a superposition of decayed and not decayed states. Its wave function spreads across both possibilities simultaneously. And here is the problem. The atom is connected mechanically to the cat's fate. The cat's life or death depends on the atom's state. So if the atom is in superposition, what is the cat? By the logic of quantum mechanics, before you open the box, the cat must be in a superposition of alive and dead, both at once. Neither definitely one nor the other. The wave function of the entire system, atom, detector, mechanism, and cat, is a single entangled mathematical object representing both possibilities simultaneously. And then you open the box, you look, and the wave function collapses. The cat is either alive or dead. Schrödinger intended this as a reductio ad absurdum, a demonstration of how ridiculous it was to apply quantum mechanics to large, everyday objects. Cats are obviously not in superpositions of alive and dead. The idea is nonsense, but the thought experiment didn't kill quantum mechanics. It killed our comfortable assumptions about where quantum weirdness ends and classical reality begins. Because where exactly does the line fall? Why does the atom obey quantum rules but the cat doesn't? At what size, at what complexity, does a quantum superposition become a classical definite state? Nobody in 1935 had an answer. Nobody has a fully satisfying answer today. The cat became one of the most famous images in all of science, a symbol of quantum strangeness, a poster for the measurement problem, a reminder that the most successful physical theory ever created contains, at its heart, a conceptual gap that no one has managed to close. Various solutions have been proposed over the decades. Each one resolves the cat paradox, but each one does so by introducing something strange of its own. Part 9. The Copenhagen interpretation and its discontents. The dominant answer to the measurement problem, for most of the 20th century, was simply to not answer it. This sounds evasive, and it is. But it was evasive in a sophisticated, principled way, Or at least that was the argument. Niels Bohr and his colleagues in Copenhagen developed an interpretation of quantum mechanics that drew a sharp line between the quantum world and the classical world. Quantum systems, atoms, electrons, photons, are described by wave functions and exist in superpositions. Classical systems, measuring devices, cats, human observers are not. They have definite states. They are classical by definition. The act of measurement in the Copenhagen view is precisely the interaction between a quantum system and a classical measuring device. That interaction collapses the wave function. How? Why? The interpretation doesn't say. That's just what measurement does. It's a primitive act, fundamental, not reducible to anything else. This is deeply unsatisfying from a philosophical standpoint. It draws an arbitrary line between quantum and classical, but gives no account of where that line falls or why it exists. It grants a special role to measurement and observer without defining what counts as a measurement or what an observer must be. Does the observer need to be conscious? Does a camera count? Does a rock? Bohr's response to these questions was essentially, stop asking. The purpose of physics is to predict the outcomes of experiments. The Copenhagen interpretation lets you do that perfectly every time. What more do you want? Many physicists found this intellectually uncomfortable but practically irresistible. The formalism worked. Every experiment confirmed its predictions, and there was always more physics to do, more particles to discover, more equations to solve, without getting lost in philosophical swamps. Shut up and calculate became the unofficial motto of working physicists. It was pragmatism elevated to a philosophy, or philosophy carefully kept at bay. But not everyone could shut up. Not everyone could resist the question of what quantum mechanics actually meant. What was really happening underneath the equations in the dark between measurements? One of those who couldn't resist was a young graduate student at Princeton. In 1957, his name was Hugh Everett. Part 10. The Many Worlds. Hugh Everett was 27 years old when he submitted his doctoral thesis. It was a quiet document, written in careful academic prose, and it proposed something that would take decades to be taken seriously, and that is still today hotly debated. Everett looked at the measurement problem and asked a simple question. What if the wave function never collapses? What if the Schrödinger equation, which describes the smooth, continuous evolution of the wave function, is simply always true? What if there is no collapse, no special role for measurement, no mysterious line between quantum and classical? If that's true, then what happens when a measurement occurs? The answer, Everett argued, is that the measuring device also goes into a superposition. And the experimenter, and the room, and everything connected to the experiment. The entire universe enters a superposition of all possible outcomes. But here's the key insight. In each branch of that superposition, there is a version of the experimenter who sees one definite outcome. The cat is alive in one branch and dead in another. The electron went through the left slit in one branch and the right slit in another. Every possible outcome of every quantum measurement happens in a different branch of the universal wave function. These branches don't interact. They don't communicate. To each observer in each branch, the world looks perfectly definite. You always see one outcome. You always find the cat either alive or dead. The branching happens, but you only ever experience one branch, the one you're in. This is the many worlds interpretation of quantum mechanics. And it is either the most profound truth ever discovered about the universe, or the most extravagant fiction ever dressed up in mathematical clothing. Physicists disagree vigorously about which. The appeal is obvious. Many worlds requires no special collapse mechanism, no mysterious role for observation, no arbitrary line between quantum and classical. The Schrödinger equation is simply true, always, everywhere, for everything. The universe is a single, gigantic, constantly branching wave function. The cost is equally obvious. You are multiplying entities, worlds, universes, versions of reality on a scale that makes the imagination real. Every quantum event that could have gone differently has gone differently in some branch. Every atom that could have decayed has decayed somewhere. Every particle that could have gone through the left slit has gone through the left slit, and also through the right slit in parallel realities that will never again be aware of each other. The number of branches is not merely large. It is incomprehensibly, astronomically, mind-bendingly vast, and growing, every moment, everywhere in the universe. Simultaneously, is this real? Do all those worlds actually exist? Everett said yes. The mathematics says they must. And Everett, unlike the Copenhagen school, was not willing to add extra physics, extra collapse mechanisms, extra rules on top of the equations just to make the multiplying worlds go away. His thesis was largely ignored during his lifetime. He left academia, worked in defense research, and died in 1982 without seeing his idea taken seriously by mainstream physics. Only after his death did many worlds begin its rehabilitation, driven partly by advances in a related field called decoherence, which offered a way to explain why we don't notice the branching happening around us. Today, many worlds has serious defenders among some of the most rigorous physicists and philosophers of science in the world. It also has serious critics. The debate is far from resolved. But the idea itself, that reality is infinitely more vast than we can perceive, that every possible history is playing out somewhere in the branches of a universal wave function, that the universe is not a single story, but an endlessly proliferating library of every story that quantum mechanics permits. That idea has lodged itself permanently in our understanding of what reality might be. Part 11. DCOHRNCE and the DISAPPRNG quantum world. If many worlds is right, why don't we notice the branching? Why does the world around us look perfectly definite, single, classical, non-branching, when the underlying quantum reality is supposedly this vast superposition of all possibilities? The answer that most physicists find convincing, regardless of their preferred interpretation, is a process called decoherence. Here is the key insight. A quantum superposition is an incredibly fragile thing. For a particle to maintain its superposition, to genuinely exist across multiple possibilities simultaneously, it must be isolated from its environment. The moment it interacts with anything, a photon of air, a vibration in the surrounding material, a stray electromagnetic field, it becomes entangled with that thing. And that entanglement spreads. The superposition leaks outward, becoming entangled with more and more particles in the environment. The result is that the superposition doesn't disappear, it grows. But it grows into something so vast, so entangled with so many particles in the environment, that the different branches of the superposition become effectively invisible to each other. They stop interfering. They can no longer recombine into a single coherent superposition. To any observer inside one branch, the world looks perfectly classical. The superposition has apparently collapsed, not because of any mysterious physical process, but simply because the coherence between branches has been diluted into the environment beyond any practical possibility of recovery. This is decoherence, and it happens extraordinarily quickly for macroscopic objects. For a cat-sized object interacting with air molecules, the timescale for decoherence is unimaginably small, far shorter than any measurement could possibly capture. This is why cats are never observed in superpositions, not because the quantum rules stop applying, but because the decoherence happens so fast that the superposition is immediately drowned in environmental entanglement. For electrons in carefully controlled laboratory conditions, decoherence can be suppressed. This is how interference experiments are possible. The electrons are isolated from their environment long enough to maintain their quantum coherence. This is also why building a quantum computer is so ferociously difficult, maintaining quantum superpositions in real physical systems, long enough to perform useful computations, requires isolation from environmental disturbance at a level that is extraordinarily hard to achieve. Decoherence explains why the quantum world appears to vanish as we move to larger scales, but it doesn't fully solve the measurement problem. It explains why the branches stop interfering, but it doesn't explain why we experience only one branch. It explains why the cat looks definitely alive or definitely dead, but not why the cat is alive rather than dead, or vice versa. The question of what selects one outcome from many remains open, and it may remain open for a very long time. Part 12. Quantum tunneling and the world it built so far, we have been living in the philosophical deep end, wrestling with interpretations, paradoxes, thought experiments. But quantum mechanics is not only a philosophical puzzle, it is an engineering tool of extraordinary power. And to appreciate just how thoroughly it has transformed the world you live in, consider one of its most counterintuitive features, quantum tunneling. In classical physics, if you roll a ball toward a hill and the ball doesn't have enough energy to climb over the hill, it rolls back. The barrier is impenetrable. Energy conservation is non-negotiable. In quantum mechanics, a particle facing a barrier it classically cannot overcome has a non-zero probability of simply appearing on the other side, not climbing over, not breaking through, appearing, tunneling through the barrier as if it weren't there. This happens because the wave function of the particle extends into and through the barrier. Even where the particle classically cannot go, the wave function has a small but non-zero amplitude. And where the wave function has amplitude, there is a probability of finding the particle. When the particle is detected, when the measurement occurs, there is a chance, small but real, that it is found on the far side of the barrier. For everyday objects, this probability is so vanishingly small as to be completely irrelevant. You will never quantum tunnel through a wall. Not because the law forbids it, but because the probability is so small that you would need to wait vastly longer than the age of the universe for it to happen even once. But for particles as small as electrons, tunneling is not exotic. It is routine. The transistor, the fundamental building block of every electronic device you have ever used, works in part because of quantum tunneling. As transistors have shrunk to nanometer scales over the decades, quantum effects have become not incidental but central. The engineers designing modern microprocessors must account for tunneling explicitly in their calculations, sometimes exploiting it deliberately, sometimes engineering around it as a source of unwanted leakage. The tunnel diode is a device built specifically around quantum tunneling, allowing current to flow through a barrier in ways classical physics would forbid. Scanning tunneling microscopes use the exponential sensitivity of tunneling current to atomic distances to image surfaces with atomic resolution, to literally see individual atoms. Flash memory, which stores data in billions of devices worldwide, uses tunneling to write and erase data. And tunneling is not only a technology. It is responsible for the existence of the sun. The sun shines by fusing hydrogen nuclei together in its core. But hydrogen nuclei are positively charged, and like charges repel. At the temperature of the sun's core, about 15 million degrees Celsius, classical physics says the nuclei don't have enough energy to overcome the electrostatic barrier between them. They should simply bounce off each other. Fusion should not happen. The sun should not burn, but it does. Because quantum tunneling allows the nuclei to tunnel through the Coulomb barrier, fusing despite their insufficient classical energy. Without quantum tunneling, there would be no fusion in stellar cores. Without stellar fusion, there would be no heavy elements. Without heavy elements, there would be no planets. Without planets, there would be no life. Quantum tunneling is not an exotic curiosity. It is one of the reasons you exist. Part 13. The uncertainty principle have been speaking of the wave function and measurement and superposition. But there is another cornerstone of quantum mechanics that deserves careful attention, one of the most famous and most misunderstood ideas in all of science, Werner Heisenberg's uncertainty principle. In 1927, Heisenberg, a young German physicist working in Bohr's circle, derived a mathematical relationship between two properties of a quantum particle, its position and its momentum. The principle states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a limitation of measuring instruments. It is not that our tools disturb the particle when we measure it, though they do. The uncertainty is deeper than that. It is built into the fabric of what a particle is. A quantum particle doesn't have a precise position and a precise momentum simultaneously. These two properties are complementary. Defining one more sharply necessarily makes the other more blurred. The product of the uncertainty in position and the uncertainty in momentum can never be smaller than a certain minimum value, given by Planck's constant. To see why, think about the wave function. A wave that has a precise, definite position looks like a sharp spike, all its amplitude concentrated at one point. But mathematically, such a spike is composed of a superposition of an enormous range of different wavelengths. And wavelength, in quantum mechanics, is directly related to momentum. A particle with a sharp position has a wave function built from many different wavelengths, many different momenta, and so its momentum is maximally uncertain. Conversely, a particle with a definite momentum has a wave function of a single, pure wavelength, a smooth, endless wave extending through all of space. Such a wave has no definite position at all. It is spread uniformly everywhere. Nature, it seems, will not give you both at once. You can pin down where something is, or you can pin down how fast and in what direction it's moving, but the more precisely you specify one, the more the other dissolves into uncertainty. This has profound consequences. It means that the very concept of a particle following a definite path through space, like a billiard ball rolling along a table, is not just unknown but meaningless at the quantum scale. There is no path. There is only the wave function, evolving, spreading, concentrating, dissolving, as the particle moves through the world. The uncertainty principle also has a remarkable consequence for the energy of a quantum system. A particle confined to a very small region, with its position sharply defined, must have a large uncertainty in momentum and therefore in energy. This means that confining particles costs energy. The smaller the confinement, the more energy is required. This is why atoms don't simply collapse, why electrons don't spiral into the nucleus. The uncertainty principle creates a kind of quantum pressure that resists confinement below a certain scale. The electron is pushed outward from the nucleus not by any classical force, but by the irreducible quantum uncertainty of its position. The atom is stable because nature refuses to let the electron's position be known too precisely. Part 14. Quantum field theory and the fabric of reality have been talking about quantum mechanics as it applies to particles, electrons, photons, atoms. But the deepest and most complete version of quantum theory is not about particles at all. It is about fields. Quantum field theory is the framework that emerges when you combine quantum mechanics with special relativity. It is the foundation of the standard model of particle physics, the most precisely tested theory in the history of science. In quantum field theory, the fundamental entities are not particles but fields. Fields that permeate all of space. The electron field, the photon field, the quark fields. A particle, an electron, say, is not a tiny ball of stuff. It is a localized excitation of the electron field, a ripple, a vibration. A knot of energy in a field that extends throughout the entire universe. When two electrons repel each other, they are not pushing against each other through empty space. They are exchanging photons, excitations of the photon field, and it is this exchange that produces the electromagnetic force. Forces, in quantum field theory, are not mysterious invisible pushes and pulls. They are the result of particles exchanging other particles, gauge bosons, that carry the force between them. This picture is extraordinarily successful. The predictions of quantum electrodynamics, the quantum field theory of electromagnetism, have been confirmed to 11 decimal places. The magnetic moment of the electron, a tiny quantum property, is predicted by theory and confirmed by experiment with a precision that is astonishing. It is as if you measured the distance from New York to Los Angeles and got the answer right to within the thickness of a human hair. But quantum field theory also revealed something unexpected about the vacuum, about empty space. In quantum field theory, the vacuum is not empty. It cannot be. The uncertainty principle, applied to fields rather than particles, means that even in a region of space with no particles, no electrons, no photons, nothing, there are still fluctuations. Random, ceaseless, unavoidable fluctuations in the quantum fields. Particles flicker into existence and annihilate each other in times so short that energy conservation is not violated, virtual particles, the physics literature calls them, though the name is somewhat misleading. These vacuum fluctuations are real. They have measurable consequences. The Casimir effect, a tiny attractive force between two very closely spaced metal plates in a vacuum, is a direct consequence of vacuum fluctuations. The plates alter the fluctuations of the electromagnetic field in the space between them, and this produces a net force. It has been measured. It is real. The vacuum seethes with quantum activity. Empty space is not empty. It never was. And this leads to one of the most embarrassing failures of modern physics, a problem so severe that physicists sometimes call it the worst prediction in the history of science. When you calculate the energy density of the quantum vacuum, the amount of energy stored in all those vacuum fluctuations, you get a number. A very large number. Enormously, absurdly, incomprehensibly large. When you compare it to the observed energy density of the universe, the cosmological constant, the measured dark energy that is causing the universe's expansion to accelerate, you find that the theoretical prediction is off by somewhere between 50 and 120 orders of magnitude. That is, the theory predicts a number that is 10 to the power of 50 to 10 to the power of 120 times larger than what is observed. No other prediction in physics is wrong by anything close to this margin. It is not a small discrepancy. It is the most spectacular failure of a quantitative prediction in the history of human inquiry. And it sits there, unresolved, at the junction of quantum mechanics and cosmology, a monument to how much we still don't understand. Part 15. The quantum mind. We have traveled from photons and electrons to vacuum energy and cosmology. Now let us take a different turn into territory that is more speculative, more contested, and in some ways more intimate, the question of consciousness and quantum mechanics. There is a reason the question arises. In the standard formulations of quantum mechanics, measurement, the interaction that collapses the wave function, is somehow special. And in some formulations, particularly early ones, the presence of a conscious observer seemed to play a role. Wigner's friend, a thought experiment by the physicist Eugene Wigner, pushed this idea to its logical extreme. If the wave function collapses when observed, and if observation requires a conscious mind, then quantum mechanics might require consciousness as a fundamental ingredient of reality. Most physicists today reject this conclusion. Decoherence explains apparent collapse without invoking consciousness. A camera can perform a measurement. A rock can interact with a quantum system and produce a record. Consciousness is not required, but the question has not entirely gone away. In the 1980s and 1990s, the physicist Roger Penrose and the anesthesiologist Stuart Hameroff proposed a theory, orchestrated objective reduction, or OR, in which quantum processes in structures inside neurons called microtubules play a role in generating conscious experience. The theory is controversial, to put it mildly. Most neuroscientists and physicists regard it with deep skepticism. The brain is warm and wet and noisy, a terrible environment for maintaining quantum coherence. Decoherence should destroy any quantum effects in neurons almost instantaneously. Penrose and Hameroff have responses to these objections. The debate continues. The evidence is not decisive. But the broader question, whether consciousness has any special relationship to quantum mechanics, whether the fact that quantum theory seems to require observers to make sense has any deep implication for the nature of mind, refuses to be entirely dismissed. There is a more subtle version of the question. Not whether the brain is a quantum computer, but whether the structure of quantum theory, with its insistence on the role of observation, its refusal to describe reality independent of measurement, its suggestion that the wave function represents not the world but our knowledge of the world, tells us something deep about the relationship between mind and reality. Some philosophers of physics argue that quantum mechanics, properly understood, is fundamentally about information, about what can be known, what can be communicated, what can be measured. And information, unlike mass or charge or spin, is not purely physical. It is always information for someone, always relative to an observer. If quantum mechanics is fundamentally about information, and information is always relative to an observer, then perhaps the quantum world is not a world of things existing independently of being observed. Perhaps it is a world of relations, of perspectives, of events occurring at the intersection of one system and another. This view, pursued most rigorously by the physicist Carlo Rovelli in his relational interpretation of quantum mechanics, doesn't require consciousness to be fundamental, but it does require giving up the idea of a single, objective, observer-independent description of reality. Every system has its own quantum state relative to every other system. There is no view from nowhere, no God's eye perspective. Reality is, at its deepest level, relational, a vast web of interactions, each one real relative to the systems involved, none of them absolutely real in any observer-independent sense. It is a picture that would have troubled Newton. It would have troubled Einstein. But it is consistent with every experiment ever done, and it resolves several of the deepest paradoxes of quantum mechanics with an elegance that some physicists find compelling and others find merely trading one confusion for another. Part 16. Quantum Computing and the Future from the Philosophical to the Practical. Because quantum mechanics is not only a source of philosophical puzzles, it is the foundation of the next technological revolution. The computer you're familiar with, the classical computer, whether it's a laptop or a smartphone or a server farm, operates on bits. A bit is a unit of information that can be either 0 or 1. Everything your computer does, every calculation, every image, every message, is ultimately a sequence of operations on bits, switching them between 0 and 1, combining them, comparing them, storing and retrieving them. A quantum computer operates on qubits, quantum bits. And a qubit, unlike a classical bit, can exist in a superposition of 0 and 1 simultaneously. It is not 0 or 1. It is a quantum superposition of both, until it is measured, at which point it collapses to a definite value. This might sound like only a small difference, but the implications are profound. A classical computer with n bits can store one of 2 to the power n possible states at any given moment. A quantum computer with n qubits can exist in a superposition of all 2 to the power n states simultaneously. For large n, this is an astronomically vast space of computation occurring in parallel. The challenge is extracting useful information from this superposition. If you simply measure the qubits at the end of a quantum computation, the superposition collapses to a single random outcome, no better than a classical computer. The art of quantum algorithm design is finding ways to manipulate the superposition so that the wrong answers interfere destructively and cancel out, while the right answers interfere constructively and are amplified. The final measurement then has a high probability of yielding the correct result. Several such algorithms have been discovered. Shor's algorithm, developed in 1994, can factor large numbers exponentially faster than any known classical algorithm. This is significant because the security of much of the world's encryption relies on the difficulty of factoring large numbers. A sufficiently powerful quantum computer running Shor's algorithm could break current encryption schemes, a prospect that has motivated enormous investment in both quantum computing and post-quantum cryptography. Rover's algorithm provides a quadratic speedup for searching unsorted databases. Quantum simulation algorithms allow quantum computers to model quantum systems, molecules, materials, chemical reactions, with an efficiency that classical computers cannot match. This last application may prove the most transformative. The ability to simulate molecular interactions at the quantum level could revolutionize drug discovery, materials science, and the design of catalysts for chemical reactions. As of the mid-2020s, quantum computers exist and are operational. Companies including IBM, Google, and a growing number of startups have built quantum processors with tens to hundreds of qubits. Google claimed quantum supremacy in 2019, demonstrating a quantum computation that would take a classical supercomputer an impractically long time to replicate. IBM has pursued a roadmap of steadily increasing qubit counts and improving error rates. But current quantum computers are what researchers call NISQ devices, noisy intermediate-scale quantum computers. They are error-prone, fragile, and limited in the depth of computation they can perform before decoherence and noise degrade the results. Building a fault-tolerant quantum computer, one that can correct errors faster than they accumulate, enabling arbitrarily long and complex computations, remains one of the great engineering challenges of our time. The timelines are contested. Some researchers believe fault-tolerant quantum computing is a decade away. Others say 2 or 3 decades. A few are more pessimistic still. But the direction of travel is clear, and the investment from governments, corporations, and research institutions around the world is enormous. The quantum computer is not simply a faster classical computer. It is a different kind of computational machine, one that operates according to the laws of quantum mechanics and can solve certain classes of problems that are, for practical purposes, intractable on classical hardware. When it matures, it will change cryptography, chemistry, materials science, and optimization in ways we can only partially anticipate. Part 17. Quantum cryptography and absolute secrecy. While quantum computers threaten current encryption, quantum mechanics also offers a solution, one that doesn't just make eavesdropping difficult but makes it physically impossible. Quantum key distribution, or QKD, uses the principles of quantum mechanics to distribute encryption keys between two parties in a way that any eavesdropping is guaranteed to be detected. Here is the basic idea. Recall the measurement problem. When you measure a quantum system, you disturb it. You collapse its wave function. This is not a technological limitation. It is a law of nature. You cannot observe a quantum system without affecting it. In QKD, one party, call her Alice, sends a stream of photons to another party, call him Bob. Each photon is prepared in one of several possible quantum states, encoding a bit of the key. Bob measures the photons and records the results. The two parties then communicate classically to establish which measurements were compatible, and they discard the rest. What remains is a shared key, identical bits held by Alice and Bob, that can be used to encrypt and decrypt messages. Now suppose an eavesdropper, Eve, intercepts the photons in transit and tries to measure them before passing them on to Bob. She must measure the photons to learn anything about them, but measuring quantum systems disturbs them. Eve's measurements will introduce errors into the photon stream that Alice and Bob can detect by comparing a portion of their keys. If the error rate is above a certain threshold, they know someone is listening, and they discard the key. No measurement, however careful, can extract information from a quantum system without disturbing it. This is not a matter of engineering. It is a consequence of the uncertainty principle and the no-cloning theorem, a quantum mechanical result that states it is impossible to create a perfect copy of an unknown quantum state. QKD is not merely computationally secure only until someone finds a better algorithm or a faster computer. It is information theoretically secure. Its security is guaranteed by the laws of physics. Even an adversary with unlimited computing power cannot break it without being detected. Quantum communication networks using QKD are already operational in several countries. China has deployed a satellite-based QKD system capable of distributing keys over thousands of kilometers. Networks in Europe and Asia are growing. The technology is not yet globally deployed, but its trajectory is clear. In a world where quantum computers threaten to break classical encryption, quantum cryptography offers a future in which privacy is guaranteed not by computational difficulty, but by the fundamental laws of quantum mechanics, by the very strangeness that has puzzled physicists since the 1920s, turned to a purpose that Bohr and Einstein could never have imagined. Part 18. The simulation hypothesis and quantum reality have arrived now at the edge of what is known, and perhaps at the edge of what is knowable. Here, where physics bleeds into philosophy and philosophy bleeds into something else entirely, there is a question that has gained increasing currency in recent years. Is the universe a simulation? This is not a new idea. Descartes entertained a version of it in the 17th century, the evil demon who might be deceiving us about all apparent reality. The 20th century gave us the thought experiment of the brain in a vat. The 21st century has given us the simulation hypothesis, most famously articulated by the philosopher Nick Bostrom. Bostrom's argument is straightforward. If civilizations commonly survive long enough to develop enormously powerful computers, computers capable of simulating conscious minds in detail, then the number of simulated minds in the universe would vastly outnumber biological minds. In which case, any randomly selected mind, yours, say, is far more likely to be simulated than biological. This is a probabilistic argument and it has holes. It assumes minds can be simulated, which is not established. It assumes advanced civilizations survive, which is not guaranteed. It assumes a lot, but it is not obviously wrong, and some serious thinkers take it seriously. What does quantum mechanics have to say? There are suggestive features. The fact that the universe is discrete at the smallest scales, that energy, space, and time may be quantized, with Planck scale limits below which nothing meaningful can be said, has a certain digital quality. A simulated universe might naturally have a smallest pixel size, a smallest tick of the clock, a maximum information density per unit volume. The universe does seem to have a maximum information density. The Bekenstein bound, derived from the physics of black holes, sets an upper limit on the amount of information that can be contained within any region of space. The universe processes information in finite, quantized amounts. It has, in some sense, a resolution limit. The holographic principle, one of the most striking results to emerge from the study of quantum gravity and string theory, suggests that all the information describing a volume of space can be encoded on its boundary surface. The three-dimensional reality we experience might be, in a precise mathematical sense, a projection of two-dimensional information, a hologram. Not a simulation, exactly, but a reality whose information content is organized in ways that challenge our naive intuitions about space and substance. None of this proves we live in a simulation. None of it was intended as evidence for a simulation. The holographic principle is a result about quantum gravity, not about programmers and computers. But the fact that the universe has these information-theoretic properties, these features that resemble, in certain ways, the properties of a computational substrate, has fed speculation. What can we say with confidence? We can say that the universe is made of information, that at the deepest level, physical reality is not stuff but relationships, not substance but pattern. John Wheeler, one of the great physicists of the 20th century, coined the phrase "it from bit," the idea that physical existence emerges from informational properties. Every particle, every field, every spacetime event derives its existence from information. From yes-no answers to yes-no questions. Whether this information is running on some substrate we cannot access, whether there is something outside the universe computing it, is a question that may be permanently beyond science. Science works by testing hypotheses against observations from within the universe. If the simulation runs on hardware outside the universe, no experiment inside can detect it. It is, perhaps, the ultimate unfalsifiable hypothesis. But unfalsifiable is not the same as uninteresting. And the fact that we can even ask the question, that the mathematics of quantum mechanics and information theory leads us to a place where such questions seem worth asking, is itself remarkable. Part 19. Quantum Gravity and the Edge of Knowledge. There is one more frontier we must visit before our journey is complete. The place where quantum mechanics and general relativity meet and fail to agree. General relativity is Einstein's theory of gravity. It describes spacetime as a smooth, continuous four-dimensional fabric, curved by the presence of mass and energy. It is spectacularly successful at describing the large-scale universe. The orbits of planets, the bending of light around massive objects, the expansion of the cosmos, the existence of black holes, the detection of gravitational waves rippling out from colliding neutron stars a billion light-years away. Quantum mechanics describes the small-scale universe of particles, fields, atoms, the forces between them. It is equally spectacularly successful at its own scale. The problem is that the two theories are fundamentally incompatible. General relativity treats spacetime as smooth and continuous. Quantum mechanics treats everything as discrete and probabilistic. General relativity is deterministic. Given the state of the universe now, the equations predict its state at any future time exactly. Quantum mechanics is irreducibly probabilistic. General relativity ignores quantum effects. Quantum mechanics ignores gravity almost entirely. In most situations, this doesn't matter. Gravity is so weak at the atomic scale that ignoring it introduces negligible error. The other forces, electromagnetism, the strong nuclear force, the weak nuclear force, are all successfully described by quantum field theories, and the resulting standard model is enormously accurate. Gravity simply doesn't show up at particle physics scales, but there are places where gravity and quantum mechanics must both apply. At the center of a black hole. At the moment of the Big Bang. At scales approaching the Planck length 10 to the minus 35 meters, where the quantum fluctuations of spacetime itself can no longer be ignored. At these extremes, our two best theories simply break down. They produce infinities, inconsistencies, nonsense. The equations stop working. The physics stops making sense. We need a theory of quantum gravity, a theory that successfully reconciles quantum mechanics with general relativity, that describes spacetime itself as a quantum object, that makes sense at all scales from the subatomic to the cosmological. We don't have one. The leading candidate for decades has been string theory. In string theory, the fundamental entities are not point particles but tiny, one-dimensional vibrating strings. Different vibration modes correspond to different particles. The geometry of the space through which the strings vibrate determines the laws of physics. And crucially, the mathematics of string theory requires a graviton, a quantum of gravity, and produces a version of general relativity automatically as a low-energy limit. String theory is mathematically beautiful. It has generated an enormous wealth of insights, including the holographic principle we discussed earlier. But it makes almost no concrete, testable predictions at energy scales accessible to current experiments. It requires extra dimensions, 6 or 7 compact dimensions curled up too small to detect. It may describe not one universe but a vast landscape of possible universes, each with different physical laws. Whether it is a theory of our universe, or of some possible universe, or of mathematics rather than physics, these are questions the theory has not yet answered. The other major approach is loop quantum gravity, which attempts to quantize spacetime directly rather than introducing strings. It suggests that space itself is not continuous but woven from discrete quantum units, loops of quantized space. Like string theory, it has produced important mathematical insights, including an account of black hole entropy. Unlike string theory, it does not require extra dimensions and makes no assumptions about matter. But it too struggles to make contact with experiment. Neither theory has been confirmed. Neither has been ruled out. The experiments needed to test them require energies far beyond any particle accelerator we can build, or sensitivities far beyond any detector we can construct. Quantum gravity remains the deepest unsolved problem in all of physics, and this is where we stand, not at the end of the story but somewhere in the middle, possibly near the beginning. Part 20. What it all means, let us come back at the end of this long journey to where we began. Close your eyes, the chair beneath you, the air around you, the darkness behind your eyelids. All of it, every atom is not what you thought it was. The atoms are not solid. They are mostly empty space, with tiny nuclei surrounded by electron wave functions, clouds of probability that have no sharp edges, no definite positions, only likelihoods and tendencies. The electrons are not little balls orbiting a central point. They are quantum objects, smeared through space, existing in superpositions of energy states, held in their atomic orbits not by any classical force but by the uncertainty principle itself. The light entering your eyes, if your eyes were open, is not a continuous stream of energy. It is a rain of photons, each one a quantum excitation of the electromagnetic field, each one's position and trajectory undefined until the moment it is absorbed by a receptor in your retina. The forces between your body and the chair beneath you are carried by virtual particles, flickering in and out of existence in the quantum vacuum, exchanging momentum between charged particles in a dance of creation and annihilation happening billions of times per second in every cubic nanometer of matter. The universe, at its finest grain, is not made of things. It is made of events, of interactions, of measurements, of information exchanged between one part of reality and another, between observation and the observed, the solid, continuous, deterministic world of classical physics, the world of Newton's clockwork universe, of billiard balls on frictionless tables, of exact positions and exact velocities and exact predictions, was always an approximation. A convenient fiction that works beautifully at human scales because the quantum effects average out over the trillions of atoms we are made of, leaving something that looks, for practical purposes, classical. But scratch the surface, go small enough, go precise enough, and the clockwork dissolves. What remains is stranger, more beautiful, and more mysterious than Newton could have imagined. We have superposition, the capacity of quantum systems to exist across multiple states simultaneously, to be in many places at once, to hold multiple possibilities in suspension until the moment of measurement resolves them into actuality. We have entanglement, the non-local connection between distant particles, defying any classical notion of locality, weaving distant parts of the universe into correlations that transcend space. We have the uncertainty principle, not a limitation of our instruments but a fundamental feature of reality, an irreducible fog of indefiniteness at the heart of every particle, every field, every moment of physical existence. And we have the measurement problem, the question that refuses to be answered, the gap in our understanding that the greatest minds of the past century could not bridge. What happens when a quantum possibility becomes an actual event? What selects one outcome from many? Is the wave function a physical thing or a description of our knowledge? Are there many worlds branching endlessly with every quantum event? Is reality relational, observer-dependent, informational at its core? We don't know. Not fully. Not yet. And this, perhaps, is the most important thing quantum mechanics has taught us about the universe. It is more than we can hold in our minds, more than we can visualize, more than our intuitions shaped by millions of years of evolution to navigate a world of rocks and rivers and predators and prey, a world of macroscopic objects and human-scale forces, can accommodate without enormous effort and constant revision. The universe does not owe us comprehensibility. It does not shape itself to fit the categories of human thought. It simply is what it is, and what it is, as best as we can determine, is quantum mechanical. Probabilistic, non-local, observer-dependent, discrete, entangled, uncertain. The mathematician and physicist Hermann Weyl once said that the objective world simply is. It does not happen. The flow of time, the unfolding of events, the sense of a present moment moving through time, these, he suggested, were features of consciousness, not of the physical world. Quantum mechanics suggests something even stranger, that the objective world in some important sense depends on observation to become definite at all. That before measurement there is only the wave function, a web of possibilities, a superposition of outcomes, a potential without an actual. and the actual only crystallizes, one possibility becoming real, at the moment of interaction between one part of the universe and another. Perhaps reality is not a stage on which events occur. Perhaps it is the events themselves, the interactions, the measurements, the moments of contact between one quantum system and another, with nothing fixed, nothing definite, nothing real between those moments. Perhaps the universe is not a noun but a verb, not a collection of things but a ceaseless process of becoming. And if that is so, if the deepest layer of reality is not substance but event, not matter but information, not being but relation, then the ancient philosophical questions about the nature of existence take on new forms. What is real? What does it mean to exist? What is the relationship between the observer and the observed, between mind and world, between the mathematics we write on paper and the universe those equations describe? Quantum mechanics does not answer these questions. It raises them in new and more urgent forms and then falls silent. The silence is not empty. It hums with the energy of the quantum vacuum, with virtual particles flickering in and out of existence, with entangled systems holding their correlations across light years of space, with wave functions evolving serenely in their vast mathematical landscapes, waiting for the next measurement, the next event, the next moment in which possibility becomes real. You are made of quantum fields. Your thoughts arise in a brain made of atoms governed by quantum mechanics. The photons that formed the images in your memory were quantum particles. The chemical bonds that hold your DNA together are quantum phenomena. The nuclear fusion that powers the sun that warmed the food that gave you the energy to think these thoughts, that fusion is made possible by quantum tunneling. You are not separate from the quantum world. You are part of it, an observer in a universe that seems to require observers to make sense. A conscious being in a cosmos that, on its finest scales, refuses to be fully pinned down. And that, perhaps, is not a problem to be solved. It is a mystery to be lived. The quantum world is not out there, in a laboratory, behind a wall of mathematics accessible only to specialists. It is here. It is the chair beneath you and the air around you and the darkness behind your eyelids. It is the substance of your thoughts and the firing of your neurons and the photons your eyes will gather when you open them tomorrow morning. It is everything. And everything, it turns out, is far stranger and far more wonderful than we were ever taught to expect. Sleep well. The universe will keep its secrets through the night, but they will still be there in the morning, patient, inexhaustible, waiting to be asked again.